Hi, everyone. I'm Neha Rungta. I'm a principal engineer in the Automated Reasoning group. I'm going to be talking today about the theory and math underneath the work in data privacy and security assurance. I'm joined today by Dan Peebles and Greg Frescador from Bridgewater Associates, who are going to talk about their use case and how they've leveraged within their organization this work that I'm going to be talking about. Before we nerd out, a few reminders. The slide deck will be available through SlideShare, and the talk will be recorded and posted on YouTube. The URLs for both will be in the session catalog. So the key takeaways in the talk. The scale and diversity of cloud applications today create a need to automate checks around access control for enterprises. This talk focuses on the use of provable security to achieve higher assurance around that automation at scale. In the first part of the talk, we'll take a peek under the hood. What is provable security with respect to access control? And in the second part of the talk, Dan and Greg will talk about their specific use cases that they've developed in Bridgewater Associates. Security is job zero. But this is what's turning security and data privacy in the cloud from an obligation to an advantage. Because the things that we need to do for good security, we need for governance, for good availability, for good operations. So the higher the bar for security, the overall goal and the overall governance improves for cloud, which is why it's moving to an advantage. And the realities of the security landscape is changing. The customer needs are changing based on the different dimensions. And different dimensions can be the data volume, the amount of compute required, and all of these scale dimensions are driving in AWS the next generation of technology and services around data privacy and security assurance. Our goal here is to say, I want to claim my cloud environment is secure, and I can mathematically prove it. And this provable security plays a role in both parts of this shared responsibility model. A lot of folks have probably seen this, where we say AWS is responsible for security of the cloud, while we want to partner with the customers for saying, what's this? How do we be secure in the cloud? And there's ways people can go and search for provable security in AWS. We have a website that gives more examples of how we are achieving security in the cloud with respect to verifying boot code and other supply chain verification work, crypto protocols. But this particular talk is going to focus on security in the cloud and how we are developing services and technologies to help folks be secure in the cloud. The specific solution that we're going to talk today about is Zelkova. So what is Zelkova? It's a reasoning engine that can soundly tell you answers about access control, which in turn enables checking security best practices, compliance requirements, enterprise-wide governance checks. An example governance check could be, hey, is it the case that access is only granted to a set of whitelisted principals? Or am I guaranteed that there is no access to requests from a specific IP range? So how would you do it? What can it do? Zelkova can audit for these types of checks. It can check for unintended misconfigurations, identify parts of the policies that lead to violations, lead to non-compliance, and also detect any changes that you've made with respect to your configurations, with respect to your access control, and say, oh, now you have this unintended privilege escalation based on the change that you've made to the policy. Where is this being used? There is this notion of provable security at scale. Last year, there was a feature released in the S3 console with an orange badge that flagged if the S3 bucket policies allowed unrestricted read or write access to the bucket. So this feature is driven by Zelkova. A lot of feedback after the release of the feature that the S3 team got and we got was, this is great, but we want to be in a situation that we can never create an open bucket. So just very recently, there was a launch of the Amazon S3 block public access feature. And here this says that enforces that the buckets don't allow public access. And this feature is available in the CLI, the SDK, and the console. The setting can be configured either at the bucket level or at the account level. Another service where Zelkova is integrated in is AWS Config. It provides Zelkova-driven managed rules. So if you go in the console and search for Zelkova, it will yield the rules that are driven by Zelkova. And it enables you to evaluate changes to resources, whether your access control policy comply with common best practices. Some examples are, do you have server-side encryption enabled on S3 buckets? Or are you restricting access to your Lambda resources? To learn more, you can read about Zelkova in the AWS security blog post. There is also a peer-reviewed technical paper that goes more into the details of how Zelkova works, which is published in a conference called FMCAD earlier this year. Coming back to what this means for enterprise governance, what we've heard from our customers is Zelkova is changing what people thought possible with regards to assurances around automations of access control checks. They can now achieve a more holistic and accurate representation of their access control. It's not, oh, am I checking one thing here, one thing there? What is it that I can do or cannot do within my organization with respect to my threat model, with respect to my governance rules, and have assurance that it is correct? So you will want to know, okay, great, what about me? What do I want as an AWS customer? I'm going to punt on that question because Dan and Greg are going to talk about what they have gotten out of Zelkova as AWS customers and how that maps to a lot of the requirements and questions that folks in this audience will have about it. So the title of the talk promised math. So I'm not going to disappoint folk. We are going to go back to the math. And I'm going to talk about the underlying math and logic that is driving Zelkova and is enabling this higher assurance. I'm going to play devil's advocate for the next few minutes a little bit. It's based on a question that I sometimes get from people in security, people who have a lot of experience in DevOps, and it's a very reasonable question. What does the math and logic get me? As a part to the answer, for the next few minutes, I'm going to assume a role of a DevOps engineer. And I'm going to write a regex-based scanner to check whether my S3 bucket provides unrestricted access to the bucket. So as I start writing my regex scanner, here's an example policy, principal star, action star. This is a pattern that I will want to add to my regex scanner to check whether or not the policy allows unprohibited read or write access to my bucket. Great, this is where I start. Oh, here is a little variation on that. It's star colon star. My regex scanner needs to be updated. I had only said action star. Okay, seems simple. I can add that. S3 colon star. We made another variant of that. Well, this is still provides unrestricted access. It's still overly permissive. So we will update our check. let's make things interesting. Here, let's add a condition, a source VPC. Now, this makes it such that it does not provide unrestricted access, because it says only the requests that come from the source VPC should be allowed. So we need to update our Regex Scanner and say, if the operator string equals is applied to the condition key, source VPC, then we are good. Our check is fine. What happens if we update the operator? In this, now instead of string equals, we're saying for all values string equals. We have to now go read into the documentation. This starts to get tricky. We have to run a few tests. And spoiler alert, this is not sufficient, because it operates on a list value. And if there is no source VPC set, then it will match. So now we have to update our Regex Scanner to say, string equals was fine, but for all values is not. Policy variables. Now we're starting to get, the richness of the features of the language is making this challenging to write a Regex Scanner. We have denies and string-like. IAM is a robust and flexible language, making it challenging to design a sound regex-based scanner. And we were just looking at one condition key. There are other things to consider. There are other condition keys, there are other operators, and then there are other constructs, not principle, not action. The moral of the story is we need a more principled approach. And nothing is more principled than logic. So this is modern symbolic logic, which was introduced by an English mathematician in 1847, and it's the foundation of all modern computing. So what is a symbolic logic formula? It's built from truth values, or constants, true and false, and variables that have unknown truth values. So here, x, y, and z are variables where we don't know what their truth values are. Operators such as and, or, and not. So this formula here says not x or y and z, which means either x is false or y and z are true, or both are true. So Boolean satisfiability checks that if there exists an assignment to the variables that makes the formula true, satisfiable. So SAT solvers check satisfiability if they generate an assignment to the variables that make the formula satisfiable. So an assignment such as x is equal to false, y is true, z is false, is an assignment that a SAT solver would generate to say, oh, this formula is satisfiable. Here's an example that says, oh, it is not satisfiable. There is no assignment to x that can ever make this formula true, which means it's not unsatisfiable. So what's the theoretical importance of satisfiability checking? This was the first NP-complete problem identified by Stephen Cook in 1971. It means that there is no known algorithm to efficiently determine satisfiability of every possible Boolean formula. So this is hard in theory. But the good thing for us is we don't care about every possible Boolean formula. So the work that's been done in the past 2 decades, we can leverage to make it efficient in practice. So a generalization of SAT is called SMT, Satisfiability Modular Theories. And the Boolean variables are replaced by other theories, linear and nonlinear arithmetic, strings, bit vector, arrays, lists. And here you have x squared minus 4, which is satisfiable because if you plug in the values of 2 or -2 for x, the formula is true. Where have modern SMT solvers been used? In a variety of applications. In microprocessor verifications, aerospace applications, protocol verification, software verification, a whole set of applications where the key here is to take the problem and turn it into an SMT formula. So great, but what is it that we built? We talked about policies and we talked about solvers. And we said Zelkova is an engine and a solution that allows us to reason about access control. So how do we go from something that looks like policies and and goes into looking like solvers. The one other aspect of this thing is, here's a policy. It's a JSON document. It has a set of statements with allow, deny statements, and has actions on which resources can be performed. So I'm going to make a claim that IAM policies is a very natural fit to logical formulas. Access is denied by default. It is granted by allow statements and then revoked by explicit deny statements. This is a very logical thing. So why do we need a symbolic representation? This is if we wanted to explicitly enumerate or fuzz or test or pen test all the possible request contexts, this is a very, very lower bound on the problem space. I'm saying, what are the possible set of principles? 10 to the 12 AWS accounts. Now, this doesn't even take into account federated principles or anonymous users, about 5,000 actions, 10 to the 13 resources. And here's the kicker, infinite number of condition keys, key values. So this is not something where we can just fuzz or test and get assurance that our policies are doing what it's doing. So if we take our imagination and say, oh, this set represents this infinite request context that we have. Given a request context, it says, for this principal action resource, is action allowed? Or for this particular principal action resource, access is denied. And what we want is, we want to ensure that the things that we want allowed are indeed the only things that are allowed. So the space of request context is partitioned, even in the infinite space, partitioned in things that we want allowed and partitioned into sets of things we don't want allowed. And this is where Zelkova comes in. Zelkova says, I'm going to create these boundaries, these guardrails, this wall that says only the things that you want in the set of contexts that you are allowed are indeed what's allowed, without enumerating the set of request contexts that you want allowed. So coming back, so we've decided, okay, it's hard to and almost intractable, impossible to evaluate all possible request contexts, so we need this logical representation. So how do we encode these policies as logical formulas? Actually, going back, here's a policy with 2 allow statements. Here's one principal has the S3 get star on a particular resource. Another principal has also S3 get star, but on an additional resource called secret.pdf. This is what it looks like when it's encoded as logic. If you read it, oh, principal is this, and action is S3 get star on resource manual.pdf. Or if my principal is AWS 7s and my action is S3 get star and resource is manual.pdf or secret.pdf, then access is allowed. So how would I check a governance rule on this? A valid governance rule is only a specific principal has S3 get star access to secret.pdf. Zelkova will translate this into logic and say, if the action is S3 get star and resource is secret.pdf, then principal is AWS 7s. Given a policy encoded in an SMT formula and the check as a logical formula itself, Zelkova uses an SMT solver underneath it to say, your policy is compliant with your governance rule. What happens if we change it? We change the principal in the second allow statement to not principal. Zelkova will come back and say not compliant. And if we look at the second expression in the policy, it says principal, which is not AWS 7s, has access to secret.pdf, which means pretty much everybody in the universe has access to secret.pdf. So how do we integrate it with services? One possible workflow is, I talked about automated threat modeling threat checking. You have a config rule, it fires based on the change to the resource. You get an SNS notification. it goes to a Lambda, which invokes another Lambda, which is the Zelkova Lambda, and you can check a holistic view of your IAM policies, your resource policies, S3, SNS, SQS, KMS, IoT device defender policies, and get a holistic view of access control. Who is using this? We have customers from a variety of verticals, from financial services. We have Bridgewater's, Dan and Greg are going to talk about their use case. From technology and media company, you saw the quote from Will Bingston from Netflix and publishing. So it applies everywhere. If some people might have seen this Wired article about how provable security is changing the space of what is possible. And I'm not going to go into this because this is where I'm going to hand it off to Greg, and he's going to tell you about how Zelkova has been modeled to meet their stringent data privacy and security and compliance requirements. So,
thanks, Neha. Hello, everyone. So, my name is Greg Frescador. I'm a security architect at Bridgewater. I'm here with my co-conspirator, Dan Peebles. We're going to talk today a little bit about our experiences with Zelkova. As Neha was saying, Bridgewater is an early adapter of Zelkova, and we're going to talk today about how that's going. But specifically, what we're going to talk about is a little bit about, first, who is Bridgewater, and why are we up here talking about Amazon technology? And then we're going to talk a bit about what we wanted to get out of Zelkova and what we actually were able to get and how that's going. And since this is like a 400-level talk, we're going to have to show a little bit of code. So we're going to talk about how to call Zelkova programmatically. And then we're going to be able to cover 2 use cases where we can show how to use Zelkova to build a kind of like a fancy badge and perimeter checker. Dan's going to do that. And then I'm going to talk a little bit later about how to use it to stop exfiltration checking. There are 3 points, though, that I'd like to get out right in the beginning. The first thing is that, as far as Bridgewater is concerned, Zelkova is the first system that we've been able to find that's been able to give us a formal and methodical way to analyze AWS policies. It's not like doing pattern checking. It's not doing like the policy simulator. Zelkova has a model of how policies are supposed to work, and it's solving them. And what that allows us to do is ask specific questions about the policies. So we can ask things like, is this particular principle, is it allowed to assume role to something? So we can ask specific questions. My third point is that Zelkova allows us to make hypothetical policies and ask questions about them, not ones that are deployed into AWS, but hypothetical ones that we're about to deploy so that we're not going to, say, deploy a vulnerability, and we could stop that early. Okay, but before we get to that, a little bit about Bridgewater. So Bridgewater is the world's largest hedge fund. We're based in Westport, Connecticut, and we have about $160 billion of assets that are under management. So we're a financial services company. We have our clients are 350 of the world's institutional investors. They're mostly things like pension funds, foundations, sovereign wealth funds that invest money with us on behalf of a much larger number of beneficiaries. Now, in order to make all those beneficiaries give them good returns, we build models and algorithms that try to model the way the financial system works and the way the global economy works. And in order to do that, we use a lot of AWS. We use a whole fleet of AWS accounts. Fleet is a nice vague word that my boss made me use to mask how many accounts there actually are. These aren't individual accounts. These are system accounts. They're used for security partitioning. We have a lot of them. It would be very impractical for us to try to go and audit, say, policies or analyze policies in each one of these accounts individually, and that's one of the reasons that AWS is going to help. So Zelkova is going to help. So what we want, like a lot of organizations, what we're looking to get is the ability to protect the data that we have. We want those algorithms and those models, we want them kept confidential. For our clients, we want their personal data kept confidential. We don't want to signal the things that we're doing that would allow competitors to front run our trades. And in general, right, what we want is to just be able to keep access control over the data that we have. In order to do that, we build security controls into all the systems that we deploy into all those accounts. And those security controls, what we're trying to find is, first of all, some of those security controls involve IAM policies. And what we want is to be able to determine whether those IAM policies are doing what we want them to do, whether the principles that we're allowing in the policies are actually the only ones that are allowed to take certain actions, whether certain resources are the only resources that we're allowed to access. Another thing that we want to get is we want to do that. We want to verify our policies are working the way we want without like unnecessary secondary effects. So we don't want to have something happen like we would go and deploy a policy and all of a sudden it would be like a VPC endpoint policy and all of a sudden every single system in the company is cut off from S3 because we made like an error. So we don't want to have that kind of thing happen. Another thing we'd like is we'd like to be able to analyze our policies in a nice methodical way. We have this fleet of accounts. We want something where we can apply a certain amount of automation and methodology and say DevOps style so that we can check our accounts and our policies and permissions in basically a methodical way. And finally, we want to do this without a lot of drama. We don't want things like some type of scanner that's going to generate a lot of false positives, that's going to page us in the middle of the night, and we don't want pager duty or anything like that. So we want basically to do it without a lot of excess false positives. Or I have this quote up here from our chief security architect, Dan Peebles, who you're going to hear from in a few minutes. And basically what he's saying there is, what we want is, we want a tool. We're going to run this tool against policies. It's going to tell us where we messed up, and then we'll fix it. That's what we really want. All right, so how does Zelkova help us? Well, Zelkova allows us to do exactly that. We run Zelkova against policies. We're going to show you in a few minutes a couple constraints. We run against policies with constraints. It tells us where we messed up. It tells us where we messed up kind of like in 4 different ways. The first thing is it allows us to detect certain ways that policies are misconfigured. So for example, if you take a policy and like accidentally put a star somewhere and allow world access, Zelkova will catch that kind of condition, and we're going to look at that in the 2 use cases. Another thing that Zelkova has that's really cool is that when it matches something, it identifies what about the policy is being allowed. So we're going to see in a few minutes this thing called a model that it returns. It tells us exactly the particular parts of a policy that are going to be allowed or denied access, and that allows us to find, like, if we need to fix something, it tells us a little bit about where to go look to fix something. Another thing it allows us to do is we can check configuration changes before we deploy them. Because Zelkova works on the policies that we give it, not just the policies that are inside, that are deployed inside an AWS account, we can use it to check a policy before we're going to deploy it in AWS. And that's going to prevent us from deploying something that would say, deploy a vulnerability. And finally, it allows us to go out and audit policies across all of our accounts. We can go to the fleet of accounts, assume role into the accounts, collect up all the policies, and then audit them en masse and in one big swoop. Okay, so before we get to that, I want to look through a little bit about how Bridgewater uses Zelkova, where it uses it. We have 2 workflows, one I'm going to call good and then one later called better. This is what the good workflow looks like. The purple box there, that's where we actually call Zelkova. The way the good workflow works, this is kind of like an assessment type workflow. The way it works is, in the top center there, whenever we're going to deploy a system, we have a bunch of security architects. The security architects build threat models against the systems that we're going to deploy. The threat model identifies helps us identify certain risks that this particular system is going to have. We design security controls that are going to mitigate those risks. Some of those security controls are IAM policies, and as a result of that, we write Zelkova constraints that check whether those IAM policies are doing what we want. So what we have basically is a threat model that's ultimately feeding Zelkova constraints into a system that's going to call Zelkova. Reading from left to right, what the good workflow does is, every time that we actually apply or deploy a policy into AWS, we have some triggers that trigger like events. So we have like AWS config rules or CloudWatch events. And what they do is they tell us, hey, something changed in AWS, better grab that thing and run it against the Zelkova rules and see if we found any particular defects. So in this workflow, every time something gets deployed, a policy gets deployed to AWS, we check it with the body of Zelkova constraints that came from threat modeling, and if any vulnerabilities were found, then what happens is those vulnerabilities go into a remediation tracking system, and eventually they get fixed inside of AWS. The reason this is called good, I say good, is because everything that we deploy can get checked this way. The problem with it is that what could be made better is that something can get deployed and there's a window of opportunity for the vulnerability to actually be in production. So that's what the better workflow is for. So what the better workflow is for is that this allows us to stop a deployment before it's actually gone into production. What we're doing here, it's the same threat modeling and constraints and checking with Zelkova, that's all the same. But what's happening now is instead of checking the policy with Zelkova after we deploy it, here it becomes part of a deployment plan, and every deployment plan is checked with Zelkova before we actually apply it. So now what happens is, if a policy has a defect that's picked up by Zelkova, instead of being applied in AWS, it goes into a vulnerability tracking system where it has to be remediated first, and the things that are actually past the Zelkova checks, those are the ones that get deployed into AWS. Okay, now, so this, like I was saying, it's a 400-level talk. We've got to look a little bit about how to call Zelkova. Zelkova has a RESTful interface. Eventually, it will have a RESTful API. I say eventually because I've been cautioned to talk about how everything is tentative and subject to change, and so I'm just going to say that it will eventually have a RESTful API. It has language bindings that allow us to more easily call that RESTful API. And so this is a sketch of what, say, like a Botto interface to Zelkova would look like. Now, Zelkova is actually active, so in Bridgewater, we call it every day, but just be aware that this particular method, check policy, is not what it will actually probably look like when it goes into production. Okay, so the parameters to this policy, the way we call Zelkova, is we specify these kind of like 3 parameters: a policy, an effect, and some constraints. Everyone probably recognizes the policy. The policy is just the JSON representation of an AWS policy. When I say policy, I don't mean just an identity-based policy. This could be a resource-based policy or a trust-based policy. So it's any one of the different types of policies that has effects and principles. Probably everyone already recognizes it. In the effect parameter is a token that tells Zelkova what type of query we're asking it to perform at this point. Up there, I say allows something. There are other types of queries. You can say allows world readability, allows world writability. But today, we're only asking Zelkova, because of these examples, we're only asking it whether something is allowed. So what is it that's the something that's allowed? The something that's allowed is the constraints. So the constraints in this call are another JSON document that lists a set of, it's kind of like a fragment of a policy. It lists some actions or principles or resources. And what we're asking Zelkova here is, hey, Zelkova, are any of those constraints permitted by the policy that's up there? And so that's how we ask Zelkova. And what Zelkova is going to do is, when we ask it, is that thing allowed, Zelkova is going to return us a Boolean value that says, true or false, something in the constraints is allowed by the policy. So in this particular case, right, we have a policy that allows S3 get objects and list buckets. And then we have a constraint that's looking for, hey, are there any list all things or put or get object ACLs allowed? So what do you think? Let everyone look at it. What would Zelkova return, true or false? Or any of the constraints allowed by the policy? So in this particular case, right, Zelkova is going to return false. And it's pretty obvious why it returns false, right? If you look at like list all star that's in the constraints, there's nothing up there in the action that looks like list all star. So Zelkova just gives us a false. All right, but of course, that means that Zelkova sometimes returns true, but when it returns true, it gives us kind of an extra benefit, right? It's going to give us something back with the true that's called a model. The model is a little example. It's kind of like a little proof by example of a case where not only is something allowed, but here's an example of one of the things that is allowed, and that's that thing that allows us to detect parts of a policy that we want to change. So here's another AWS policy. Right, in this case, we're looking at we're looking for an action of S3 list star and get star. We have some constraints that are asking, is list all star, is it something that's permitted? And in this particular case, we ask it, and Zelkova returns true, yes. And in fact, if you look down at the actions, right, we can see that list all star matches up with list star. And Zelkova also tells us, for example, what bucket the particular action was allowed on. Something that's kind of curious here is that Zelkova returns inside of the green statement, green action statement there. It says S3 list all. There's no actual action, right, in AWS that's called list all. What's happening here is that list all is the solution that the SMT solver gives us. Zelkova knows about the inventory of actions that are inside of AWS, but it returns to us a solution in terms of the policy that we asked about. We're asking Zelkova, are any of these constraints allowed by that policy? And in this particular case, the match, the solution by the SMT solver is list all. And what this means is that whenever we call Zelkova, we're always going to get consistent results, regardless of what's going on inside of AWS. So for example, in AWS, if they increase the inventory of actions, this query is always going to return to us the same results. Okay. So that gives us enough basic Zelkova to be able to talk about two use cases. In the first use case, Dan is going to build us basically a badge for a bucket and a perimeter checker, and I'll be back in a little while to talk about using Zelkova to prevent data exfiltration. So this is Dan Peebles.
Hi. Thank you. All right, thanks, Greg. Yeah, I'm going to talk a bit about this perimeter checker. Quick thing about myself, I'm a software developer. I've been about 6 years at Bridgewater. I've actually been longing for Zelkova for a lot longer than it's existed, I think. I've been moaning at our account team that it wasn't there until it appeared, and then I was very happy, and I think became the first actual external customer for the ARG tooling. So what I'm going to do here is to talk about the perimeter scanner, which is this looks different from which is in some ways a generalization, and in other ways a sort of refinement of these S3 badges that they have on the console today. And so the idea here is that IAM rules everything in AWS. Your entire account is controlled by IAM policies, sometimes more visible than others. S3 is one example of that, but there are many others, SQS, SNS, your KMS keys. They all have policies attached to them. Your principals have policies attached to them. We're mostly going to focus on resources here and talk about sort of the getting badges in more places. And so what we're going to talk about as a quick example is Lambda and KMS. The thing generalizes to pretty much anything that has a policy, and there are many, many resources to do. And the question we want to ask here is, can any outsider access our data? And the key distinction here from the badges on the S3 buckets that are live on the console is the badges are basically saying, can all outsiders access our data? And we want to talk about any outsiders. Now, any outsiders is, in many ways, for a sort of security-conscious organization like Bridgewater and probably many others, we care about a lot of insider threats. And so our own employees know more about our resources. And we also care about any single one of them. So if Greg turns evil one day, for example, and he opens up one of our resources to his home AWS account, that's just as concerning to us as if it's open to the world. Now, it's a little more tricky to talk about any versus all, and one of the reasons why this is sort of a complicated problem is like actually defining what outside means, because we don't want to say any outsider or any person. We want to say any outsider, and the definition of outsider will vary from people to people. And so one customer might consider outsiders to be a certain set of accounts. or anyone outside of that certain set of accounts. Others might have other definitions, and I'll go more into those definitions later. And so this tool, the perimeter checker, is not just asking can anyone do it, but also we want to know who can do it and what can they do and what can they do it to. And so we want to consider the various access patterns. There are a lot of different access patterns for AWS resources. A lot of them are authenticated, but some of them aren't. S3 as the most obvious example of that, but API gateways and things can be unauthenticated. A lot of times it happens through networking controls, so a lot of things can have a source VPC or source VPCE condition key. We want to catch those because those things get used a lot at Bridgewater and probably other places. CIDR block checks, a lot of companies do that. And a large category that I'll go more into detail about is other AWS services operating on our behalf, which adds a whole interesting layer of considerations that might not be obvious. And as we've said a few times, and Greg and Neha have said, we want excellent signal-to-noise ratio. Like it's all too easy to write the pattern-based checker that is sort of conservative and says, well, I'll just call out anything that I can't understand. But then your operations people will stop paying attention to your tool because they say, well, this thing just fired off 500 false positives, and most of them are stupid, and I'm just going to stop looking. So we want good signal-to-noise ratio. And we also don't want to lose sleep over like a clever adversarial attacker coming up with some policy that would evade the patterns that we've developed, because, as I said, we're concerned about insiders. So what we have here as our example is a couple of policies. There's a KMS key policy and a Lambda invoke policy. The Lambda invoke policy is usually not super visible on the console. It's available through APIs and SDKs. I think the console shows it as like a pretty graph of things, boxes connecting to one another. But it's the same thing. Behind the scenes, it's an IAM policy. Just as I said, everything is governed by IAM policies, almost everything. KMS key policies, you can find those on the KMS console. They sort of combine with grants in interesting ways, which I won't go into here, but add some complication there. But I'm going to sort of walk through what it means to scan the perimeter of these two policies. And so the perimeter, we can imagine that these two policies live in an account called 345. I'm not going to go with full 12 digits for obvious reasons. And they have a couple of allow statements each. And I want to phrase a question to Zelkova to ask, can an outsider access these or do things to them? So going back to the constraints thing that Greg showed us, this is the constraint I'm going to hand Zelkova, along with the policies, which I'm going to leave out briefly here, and say something like, not principals, so anyone outside of account 345, let me know if that is possible. So it's actually a very simple question. That's one of the things we like about Zelkova, is it allows us to phrase these questions in a very simple language and show me if my policies allow something. So let's just look at them real quick. So the one on the left has two allow statements. The first one is role admin in account 345. That is actually in account 345, so that's a false from Zelkova. And the second statement is also a false, because it's a user Bob also in 345. So we'd expect Zelkova to say basically no, the policy on the left does not allow something. Now the one on the right is a little more interesting, and seems to have regained some invisible characters there. But the one on the right is more interesting, not because of the invisible characters, but because of the second statement. The first statement is also in account 345. The second statement is saying allow API gateway to invoke my function. And it's a very common use case. API gateway plugs into Lambda beautifully. That's how it works. We all use it for nice serverless things. But this statement, Zelkova is actually going to say that this statement does allow something outside of 345. And it's true. API gateway is presumably not hosted inside my account. And so the question now becomes, is that OK? And so is it OK? Let people think about it for a while. OK, you thought. And I'm going to claim that it's actually not OK. And I'm going to call it a confused deputy problem. And this is a word that comes up in various places in security. But I'm going to talk about it in this context a little bit. And this is a quick sketch of what it means to be a confused deputy. Bob, honest Bob, allows Alice, a deputy, to do something to Bob's resource, and so grants Alice the permission to act on his behalf. And if we look back here a second, this is exactly what's happening, where whoever wrote this Lambda policy granted API gateway, his deputy, or her deputy the ability to call his function. So the question is, then later, at some later point in time, Alice, the API gateway, acts on Bob's resource, calls the Lambda, and everything is good. So a naive Bob is actually none the wiser that his function is misconfigured. And at some other point, Trudy, who knows about this misconfiguration, Trudy the intruder, traditional names, actually goes and calls Alice and has Alice act on Trudy's behalf on Bob's resource. And so Alice, the API gateway in this case, is actually confused because Trudy is convincing Alice to do the wrong thing. And so what I'm going to say here is it's a very common concern in AWS, mostly called out as such for SDS external ID for assume roles. If you're granting a third-party partner or something to scan your account, that's a very common case. But it also applies to AWS services themselves. And there's a lot of different ways for AWS services to call each other. And so I'll go into a little bit of what that is. So for example, the simple email service can call S3. And it's a very common use case. It's really fun. You just say, whenever you receive an email, I want it to drop the email into my S3 bucket. And one of the beauties of AWS is that they dog food everything. And so that S3 bucket doesn't magically grant SES access to the S3 bucket because it's Amazon. It's, if I want SES to be able to do things to my bucket, I say, hey, bucket policy, allow SES into it. Now, when you say allow that SES into it, SES is a deputy. It is acting on a bunch of customers' behalves. And if you don't do that properly, it'll allow other people's SES emails into your bucket. And that's often not desirable. I'd assume mostly not desirable. And there's a lot of other ways in which these things can be woven together. Like all of them create this sort of beautiful sort of serverless fabric. You can say SES use my KMS thing to encrypt these emails. That's another nice integration that they have. And you can say S3 call my Lambda when an object appears there. All of these have policies behind the scenes, and all of them are governed by saying that the KMS allows the SES to encrypt things, and the Lambda allows the S3 bucket to call it. And all of these are deputies that can be confused. And so in some cases, you might not actually care that the deputies can be confused, but you should at least know about it and make that a deliberate thing and measure it against your threat model or something like that. And there are countless others of these. There's all these services, Glacier, Secrets Manager, SNS, SQS. They all have resource policies. They can all be configured this way. They all plug in very nicely together. There's a ton of really cool features of plugging one service into another. And that's a great thing. We don't have to create servers and manage servers to plug these into one another. But on the flip side, it's a lot to think about as a security professional. You want to make sure that nobody else is calling your resources, or bad things could happen. So what the perimeter scanner does is actually a very simple, small code base. I'm sitting on top of Zelkova because Zelkova is doing all the heavy lifting. And it effectively encodes all safe access patterns for our resources. And everything that has a resource policy is in there. And we encode a whole bunch of sort of idiosyncratic ways in which all these things work. And so, for example, if a service calls SQS, your allow statement must, in some way, check for source ARN. It doesn't have to be a literal check for source ARN. You can have allow everything and deny everything that doesn't check for source ARN. That's one of the beauties of Zelkova. I don't have to think about that anymore. I just say, if a service calls SQS, source ARN must be a known ARN pattern from one of my accounts or an account that I trust. If it isn't, then someone else can drop messages in my SQS queue and probably wreak havoc on my invariants and how my stuff works. And if you're concerned about insiders who might know about these SQS queues, or even outsiders who might just be fuzzing things, because you can throw a lot of fuzzy API calls at other people's accounts and try to find out what they have. You must be checking the source ARN, otherwise your SQS queue is going to allow someone else to write to it. If SES calls S3, the example I used before, the AWS refer condition key must match known account IDs. The refer obviously has a typo in it because it always will, thanks to HTTP. But you must be checking against known account IDs when you allow SES to call S3. If API gateway calls Lambda, it also uses source ARN, but it must match a known ARN pattern. If it doesn't, your Lambda is unsafe. And so, for example, in the example I had earlier in that policy, the problem there is I created a nice serverless system that has an API gateway calling my Lambda. And Greg finds out about that and sets up his API gateway to call my Lambda 2. And so bypasses any kind of front-end protections I have there, bypasses parameter validation, bypasses custom authorizers, all the cool things you can do in an API gateway. If you don't check for that confused deputy, you're allowing someone to just completely bypass that. And that's probably not what you want. And, or even if it is OK with you, you should know about it. If S3 calls KMS, this is a very different one. It will set KMS via service to s3.star.amazon.aws. That will be the region. And the important part here for confused deputies is the encryption context S3 ARN will be set to the bucket that called it. And there are many, many, many other examples. Like, these are all documented. It's really nice. Like, you can go through the documentation, and I did it, and that's basically how I built this. But I don't want to have to think about that. Like, I spend a lot of time staring at policies. I've been doing it for years now, and I still mess these things up. Like, when I actually ran this against some of our accounts the first time, it found a whole bunch of things that I had written as the IAM expert, and it told me a whole bunch of things that I'd screwed up that I didn't even realize I'd screwed up. So like, don't assume that just because you know IAM, you're getting this right. Like, the tooling is actually extremely valuable. It's found a lot of really good stuff. And as I mentioned earlier, like the definition of outsider will vary from company to company. In many cases, you'll have a fleet of accounts of unspecified number, but you might also have partners. You might have like a third-party scanner who's allowed into your account. You don't want your people to get paged because that scanner's there, so we allow to specify what an outsider actually means to you, and that'll vary from company to company and also from account to account. Like, my prod account probably doesn't want some random trial service getting into it. My sandbox accounts might. And so with that, I'm going to pass back to Greg, who will tell you about another use case.
Great. Thanks, Dan. So one more use case. Remember back when I was talking about the better workflow where we could use Zelkova to prevent the deployment of some particular vulnerability in an IAM policy. What we're going to look at here is how to get Zelkova to answer the question, does this IAM policy I'm about to deploy, does it create a risk of an exfiltration? Does it create an exfiltration vulnerability? So in order to do that, first I have to have a quick definition of what I mean by exfiltration. Let's say that if I have a bucket and the bucket's called MyCorp stuff, if I'm reading and writing, I'm in MyCorp, if I'm reading and writing to the MyCorp stuff bucket, that's not an exfiltration risk. I'm allowed to do that. If I'm reading from some other bucket, let's say out on the internet, some random S3 bucket, that's also not an exfiltration risk. There's an exfiltration risk whenever I'm allowed to write from my corporation to some third-party bucket, to some other bucket, because I can use that channel to exfiltrate data. And so that's what this Zelkova constraint is looking for. It's basically saying, hey, if there's a policy out there that allows an action other than get object, that's a read, other than get object, to a bucket other than MyCorp stuff, then this particular policy is creating an exfiltration risk. Now, why would I care about these exfiltration risks? Suppose I'm using open source software. I say maybe I get some JSON, some JavaScript library from NPM. I'm using server-side JavaScript. When I run this particular library, all of a sudden there's malware embedded in the library. And what it's doing is, inside of my account, it's exfiltrating data out to some other corporation's bucket. That would be an example of why I want to guard against having exfiltration. I want a policy in place that prevents me from writing to third-party buckets. Okay, so here's a policy on the left-hand side that actually prevents exfiltration. What it's doing is, it's basically saying, hey, the only buckets on the left, the only buckets we're allowed to write to, we're allowed to access with S3 is MyCorp stuff. On the right-hand side, I have a change to the policy that's on the left. And what I've done is I've added an exception for a new bucket called the Starport Layer bucket. What the heck is that thing? Well, this is a great example of how Zelkova can help us detect changes that are going to introduce a vulnerability. If we're using a policy that's like the one on the left, one thing that could happen is someone may come around and say, well, I want to use a new system. I want to use, say, like the Elastic Container Service. Well, the Elastic Container Service, it uses the Elastic Container Repository to store Docker images. And the Elastic Container Repository, guess where it stores its Docker images? it stores it in this bucket called starport layer bucket. Actually, it's a suffix, but starport layer bucket. So what will happen is your ECS deployment will fail, and someone will come around and say, oh, I need an exception for this policy. I need the exception to allow access to the starport layer bucket, and we might be tempted to write the policy like I did on the right-hand side. If you look at that policy, does that policy prevent exfiltration? Well, instead of trying to guess, let's just ask Zelkova. Zelkova looks at the policy and says, hey, the one on the left-hand side policy does not allow exfiltration. The one on the right does allow exfiltration. And why? Well, it says in the model that it returns. The model says it's allowing any S3 action to basically a starport layer bucket. And so what's happening here is, if we could find a way to get Zelkova to check that policy before we actually put it into production, then we'd be able to prevent a vulnerability from occurring. Okay, so how would we do that? Well, earlier I was showing kind of like a workflow where whenever we deploy a system, we create a threat model that builds up some basically Zelkova constraints that we're going to check against our policies. What we do is we build a library of these constraints for all sorts of different checks for policies that we want to have maintained, some of which are saying, for example, in this case, we don't want principals that are outside our corporation to be able to access our S3 buckets. There are other constraints that say, hey, we don't want any, we don't want exfiltration risk. We build up a library of these, and then what we're going to do is we're going to put that library into a workflow that kind of looks like this. What's happening here is, on the left-hand side, whenever we deploy an IAM policy into AWS, we do it using a DevOps-style system. And the system is based on Terraform. Now, if you're not familiar with Terraform, Terraform is kind of like CloudFormation, except it's kind of cross-platform. So think of CloudFormation, all right? Whenever we deploy an IAM policy, we deploy it with Terraform, but we require that the Terraform be checked in to a development branch of Git first. Everything that's checked into that development branch is scanned by Zelkova. If the policy that's been checked in, embedded into Terraform, passes the scanning, it's promoted into a production branch back in Git. And then everything from that production branch is deployed into AWS. But if Zelkova fails the check from the development, that's from the code that's checked into the development branch, then what Zelkova does is it kicks the Terraform back into Gerrit's basically a tracking system. It kicks it back into Gerrit where the developers have to fix it before it will be promoted into the production branch. And so what we've done here is we've kind of found a way to implement that better workflow by using a dev and production branch inside of Git and Gerrit. And we can prevent vulnerabilities in our IAM policies from being deployed into production. Okay, so to summarize, Bridgewater, we have a lot of security controls. Some of those security controls involve IAM policies. What Zelkova gives us is the ability to check those IAM policies in a formal and methodical way. Zelkova is very thorough. What Zelkova does is, Zelkova never allows a situation where a crafty evildoer can be crafty and find a way to like combine not resource, not principal statements inside an IAM policy and find a way to like trickily get around the Zelkova checker. The SMT solver in Zelkova is never going to be fooled. It's always going to find an answer or a non-answer to the query that we're asking. And finally, what Zelkova gives us is the ability to deeply understand the policies that we're writing. Whenever we deploy a policy, we can check it with Zelkova. Basically, it's kind of like a little game, right? We kind of propose, does this particular policy allow a type of action? We ask Zelkova, it says, oh, yes, and then we understand better about how our policies actually work. And so with that, I'm going to turn it back over to Neha, and she's going to tell you a little bit more.
So in a way, you heard about how we can take provable security and apply it to enterprise-wide governance from the use case from Bridgewater. But hopefully it resonates across a lot of organizations, a lot of enterprises. We have a couple of other talks, one featuring Goldman, another one from LogMeIn. We're also going to be talking about their use of Zelkova and their enterprise governance. And there is a talk on Thursday that's using provable security, but using it for EC2 networks and talking about how it's integrated in the inspector service, using and answering questions about reachability of your EC2 networks. And if you want more, Zelkova is available for a private beta. Please talk to your friendly account manager, your TAM. I'm going to be at the security booth today at 11:30. Please come up. I'm happy to answer more questions. And also, there's a huge set of use cases developed by Bridgewater and the others in the beta community that folks can use. And thank you very much. Please remember to complete the session survey in your mobile app.